Hello and welcome. Today we're diving into a huge question in the world of cloud-native apps. How in the world do you handle data that needs to stick around in a system like Kubernetes, which is, built to be completely disposable? Let's figure it out.
So, picture this. You've got your app containerized, it's scaling like a dream on GKE, and then a pod crashes. Poof, it's gone. What happens to its data? That's the core problem we're solving today. How to give our apps a permanent memory in a system that's designed to have amnesia.
We're going to tackle this just like an architect would. First, we'll really define the problem we're up against. Then, we'll cover the absolute must-know Kubernetes storage concepts. After that, we'll look at the specific tools you have in your GCP toolbox. We'll bring it all to life with a real-world example, and then wrap everything up with a super simple guide to help you make the right call every single time.
So here's the fundamental conflict, right? Kubernetes is just brilliant at managing stateless applications. It can kill, restart, and move pods around wherever it needs to for the best efficiency. But your databases, your user uploads, all those critical logs, that stuff has to survive long after a pod is gone. This is where our stateful architecture has to begin.
So how does Kubernetes even begin to solve this? Well, it does it with a really clever layer of abstraction. Before we even think about specific services in the cloud, we have to get our heads around this universal language of storage. It's a system that neatly separates what your application asks for from the actual physical thing that provides it.
The first piece of that language is the persistent volume, or PV for short. Honestly, the best way to think about a PV is just as another resource in the cluster, kind of like CPU or RAM. It's a real chunk of storage, like a network's disk, that an admin has set up and made available for apps to use.
Okay, now here is where it gets really smart. Your application doesn't just go and grab a PV directly. No, instead it creates a persistent volume claim, a PVC. And this is the magic. A PVC is basically a claim ticket for storage. Your app just says, hey, I need 100 gigs of fast storage, and it hands that claim ticket to Kubernetes.
So who or what fulfills that claim ticket? Well, that's the job of the storage class. The storage class is the engine that makes this all happen automatically. It defines different types or classes of storage you might have available, like fast SSD, or maybe cheap archive. When a PVC comes in asking for a certain type, the storage class goes and automatically creates a matching persistent volume for it. It's like a helpful concierge for your storage needs.
And this brings the whole automated flow together. It all starts with your pod, which includes a persistent volume claim. The storage class sees that claim, it talks to your cloud provider, in this case GCP, and provisions the actual physical storage as a persistent volume. Finally, Kubernetes binds that PV to the PVC and boom, the pod can use it. It's a beautiful, decoupled system.
Okay, so we've learned the abstract language that Kubernetes speaks. Now it's time to connect that language to reality. Let's open up our Google Cloud Toolbox and see the actual physical storage options we can use to make good on all those persistent volume claims. Inside GCP, we've basically got three main players for this game. First, you can think of persistent disk, like a super fast, dedicated hard drive that you plug into a single machine. Then there's file store, which is more like a shared network drive, where lots of machines can read and write files all at the same time. And finally, cloud storage, which is a totally different beast. It's like a massive, practically infinite media library for all your files and objects. Let's take a closer look at persistent disk. This is your go-to, your workhorse for anything that needs raw, high-speed block storage. Think databases. The key thing to know here is its access mode. Read, write, once. And this is critical. It means that a disk can only be attached to a single pod at a time. This is what guarantees data integrity for those apps that just aren't built to share. But what if you need multiple pods to read and write to the same place? Well, that's exactly what FileStore was built for. Its superpower is the read-write-many access mode. This is absolutely perfect for something like a bunch of web server pods that all need to access the same shared content, or maybe a content management system where different pods are all working on the same media library. And finally, we have Google Cloud Storage, or GCS. Now, the most important thing to get here is that you don't typically use GCS with a persistent volume claim. It's not a file system you can just mount. Instead, your application's code uses the GCS API to directly upload and download objects. This makes it the perfect choice for storing huge amounts of data. Think user videos, database backups, or massive data sets for analytics.
Okay, that's enough theory. Let's make this real. We're going to design a simple little microservice that has a couple of very different storage needs, and we'll see exactly how all these different tools fit together to get the job done.
So part 1 of our app is a database. Could be PostgreSQL, could be MySQL, doesn't matter. What matters is its one critical need. It needs exclusive, high-performance, direct access to its data files. It can't share its storage with anyone else, and speed is everything.
The choice here is a no-brainer. Our database pod is going to create a PVC asking for read-write-once block storage. The GKE storage class sees that request, and it provisions a Google persistent disk. That disk then gets mounted exclusively by our database pod. It's a clean, simple, direct line for maximum performance. Okay, next up, we have a media processing service. This service runs as multiple copies or replicas, so it's highly available. And it has 2 very different storage jobs. First, it needs a shared workspace for incoming files that all the replicas can get to. And second, it needs a way to archive those files for cheap, long-term storage once it's done with them.
For that first requirement, the shared access, the clear winner is FileStore. All of our media pods will use the exact same persistent volume claim requesting read-write-many access. That PVC gets fulfilled by a FileStore instance, which gives all the pods a shared file system where they can all work on the uploaded files together.
And for that second requirement, the archival part, we're going to bypass the whole PVC system. Once a file has been processed, our application code will just make a direct API call to a Google Cloud Storage bucket. This lets us move that big file off our active high-performance file store and into a much more cost-effective and durable foam for the long haul.
All right, we've looked at all the individual pieces and seen how they can work together in a real application. So now, let's pull it all together into a final decision guide you can use for your own projects. But before we get to the final chart, you have to remember this. This is so important. Choosing the right storage type is only half the battle. The other half is your backup strategy. Seriously, a plan for backups and disaster recovery isn't just some nice-to-have. It's a core requirement for any stateful application you're serious about.
This table really brings it all home. The logic is actually pretty simple. If you need single-pod, high-performance block storage, think databases, you're going to use persistent disk. If you need multi-pod, shared file access, like for a CMS, you're going to use FileStore. And for any large objects, backups, or archives, you should bypass the PVC model and have your application call the Cloud Storage API directly.
So if you only remember 3 things from all this, let it be these 3 rules. 1. Always use the Kubernetes PV and PVC abstraction layer. It's there for a reason. 2. Map your PVCs to the right tool for the job. Persistent disk for block, FileStore for file. And 3. For those big objects and archives, just use the Cloud Storage API right from your app.
You know, understanding these patterns is really what separates just making an app work from architecting a system that's truly scalable, resilient, and cost-effective. So the final question to ask yourself is this: is your storage architecture really ready for what's coming next?